Hi guys, welcome to your 1.9 notes on patterns, equations, and graphs. By the end of the day, you will be able to use tables, equations, and graphs to describe relationships. Now, an equation is like a balanced scale. When we have an equation like x plus 8 equals 10, for example, we can take this equal sign and use that as the center of our equation that's saying that this part, this x plus 8, this part balances with 10 over here. So imagine we had some sort of box, right? We have a box worth 10, however that is. We have another box that weighs 8, and we have another box that weighs x. And we know that when we put this x box with our 8 box, that balances with our 10 box. So we want to figure out, okay, well, how can we balance it? So let's take away 8 from each side. If we take away an 8 box from each side, we're left with just 2 on one side, or sorry, 2 on the side and 2 on this side. So we know that x equals 2. And what that looks like is we minus 8 from both sides, minus 8 on both sides. That gives us x equals 2. So we know that our x box weighs 2, essentially. Let's say that instead of x plus 2, we have x times 2. Or rather, I'm going to rewrite it. I'm going to say 2x. Let's say we have 2x, and that's equal to 24. Okay, so on the one side of our balance, we have an x box, we have another x box, and on this side, we have a 24 box. Now, we don't know exactly what our x box is, but we know that 2 of them equal 24. So what we can do is we can cut each side in half. So we can take away an x, we can take away half of 24, that'll give us 12, right? And thus that x equals 12. So essentially what we're doing is we'll divide this by 2. We divide 24 by 2. As long as we do it to both sides, we get that x equals 12. I've been putting these in boxes, huh? So our x box on this case is weighing 12. Now today we've so far only been working with one variable, an x variable. But guess what? We can use 2 variables. We can use an equation. No, just kidding. Yeah, that's right. We can use an equation. Sorry, I looked ahead at the next blank. We can use an equation with 2 variables to represent the relationship between 2 varying quantities. So varying, remember, it changes. That's what a vary means, is that it changes. So changing variables. For example, let's go revisit this guy. Let's say that we don't know that this is 24, but we know that it's y. We don't know how much that's worth. We can replace this with y, and we know that x is equal to y over 2. So we can use an equation to write a relationship between 2 different variables. Now this case, because we're dealing with 2 variables, that's going to be kind of our key idea of the day. If we're dealing with 2 variables, that means our solution is going to have 2 values in it. So a solution of an equation with 2 variables, x and y, is going to be an ordered pair. Look, it has 2 quantities in it. Isn't that so cool? I think it's cool. For example, if we looked at this guy, a solution to this equation would be like 2, 4. Because here our x is 2, so we say 2 equals 4 over 2. That fits. That would be a solution. So let's check. Is 310 a solution of this equation? So 310, that's going to be our x, y. X always comes first because it follows the order of the alphabet. So here we go. Let's plug in 3 for our x. and plug in 10 for our y and see if that's true. We don't know yet, so we'll use a question mark. Is it true that 10 equals 4 times 3? Again, we took 3 for our x, plugged it in. We took y, or 10 for our y, plugged it in. And that'll simplify it just a little bit. Is it true that 10 equals 12? No, this is not true. So it's not a solution. Dang. Because it doesn't balance the scales. If we had a scale right here with our equals guy, and on this side we had 10, and on this side we had 4 times 3. Oh no, that would actually weigh a little bit too much. So it would like sink down a little bit. This would go higher. This is heavier. And our balance would be like this. It is not equal. We can even be like, no, that's not equal. Ha! It's not a solution because they're not equal. What would a solution be? A solution could be 20 equals 4 times 5, right? So our solution here, our y is 20, and our x is 5. So a solution to this equation would be the point 5, 20, because this is true. So again, a solution is two values of the variable. Here, 5 is our x, 20 is our y, and this point, this pair right here, makes the equation true. So here you have, this is actually a true story. I have two friends, Renee and Allie, and they have the same birthday. They were both born on September 25, which was just this past week, so that was exciting. However, Renee was born 2 years before Allie. So let's represent their relationship in a bunch of different ways. We're going to represent their relationship in a table. We're going to represent the relationship in an equation. And then finally, we're going to represent their equation, their relationship in a graph, and not their relationship as in their friendship, but the relationship between their ages in a graph. And I put graph paper in there already for you guys to keep your lives neat and to save us some time. Okay, so let's make a table. Let's put Allie's age here and Renee's age there. A stands for Allie, R stands for Renee. So A is Allie and R is Renee. There you go. Okay, so when Allie was born, she was 0 years old, and Renee was 2, because Renee is 2 years older than Allie. Awesome. When Allie was 1, Renee was 3. When Allie was 2, Renee was 4, etc., etc. Right? You got it. We could keep going, but it's pretty linear, simple pattern to follow. Okay, cool. Now let's write an equation. Let's say that x is Allie's age, and let's say that y is Renee's age. Then we can say that Renee's age is Allie's age plus 2. Because if you want to find out how old Renee is, you just take Allie's age and you add 2 to it. Is this the only possible equation we could have? Absolutely not. You could have said, Allie's age is Renee's age minus 2. That also works. Or you could say Renee minus 2 years is Allie. That's totally fine as well. You could say that Renee is 2 plus whatever Allie is. You notice these are all what we call equivalent equations. They're all the same kind of deal. They all mean the same thing. But there you go. Oh, we need to put our final answer in a box, guys. Ta-da! We did it. Okay, now let's put it in a graph. So we can either use the data in our table, or we can use the data in our equation to graph it. Let's go with the table. So we'll put Allie's age at the bottom, because it comes first alphabetically. So Allie's age is here in years. And then here we have Renee's age, also in years. Okay, so going along our x-axis down here, these are all of Allie's ages in years. I can make that a little bit thicker. There we go. And then going up the y-axis right here, we have Renee's age. And we're going to plot some points that go with it. So when Allie was 0, Renee was 2. So that goes at 0, 2. And when Allie was 1, Renee was 3. When Allie was 2, Renee was 4. I don't know if you heard that. That was the dog sighing. There you go. We have a bunch of points to connect them. We can also connect these points with a line. Ta-da! There it is. So here we go. There are 3 ways to represent the same kind of information. We have a table with like a X, Y, or in this case an AR column. We have an equation, which again is which is an expression with an equal sign, a statement with an equal sign. And then finally we have a graph, which is like a picture. That's literally what graph means. It means to draw or to write. Our final term of the day is called inductive reasoning. Inductive reasoning is when you is when you induce. Isn't that helpful? I know it's not helpful. Basically, it's when you have some information and then you follow that pattern to make another inference, to make another conclusion. We're going to do this in this example right here. So here I have this beautiful little tile pattern. It's got 9 tiles, and in the very middle is a blue tile. So we want to explore the relationship between the number of blue tiles, which will be our X on our graph, the number of blue tiles, and the total number of tiles, which will make our Y. We do this because the number of blue tiles comes first, and then the number of total tiles comes second in our chart. So in our first iteration, in our first step, we see we have 1 blue tile and 9 total tiles. Here we have 2 blue tiles and 18 total tiles. So here we have 3 blue tiles and 27 total tiles. Are you starting to notice a pattern? I would hope so. So here each time we add 1, this time we add 9. So let's follow that same pattern. As we add 1, as we add 1, we add 9 again. And as we add 1, we add 9 again. And 27 plus 9 is 36. We're going to add 1 again, 5, and then add 9 again. We get 45. To follow the same pattern, I'm going to keep going 6, 7, 8. And then we find 45 plus 9 is 54. Plus 9 is 63. Plus 9 is 72. So what's the total number of tiles in a figure with 8 blue tiles? 72. Now that was on a table. Let's see if graphing it will give us the same answer. So let's take our number of blue tiles and we'll put them along the bottom down here. So we'll label that number of blue tiles. Now I noticed that this has 16 bars across, but we only need to get to the 8th level, so I spaced out my tallies, my little tick guys, just to make it look easier, to look neater. And then here I noticed that we have 36 tick marks all the way up this graph, so I said that each tick mark is worth 2. So this is 2, 4, 6, 8, but then I only labeled every other one just to give myself some space. The point of a graph is to look neat. So we took the total number of tiles, and that goes up the y-axis, up this way. So if we have 0 blue tiles, we have 0 tiles at all. Awesome. If we have 1 blue tile, we have 9 tiles. If we have 2 blue tiles, we have 18 tiles. And if we have 3, we have 27 tiles. Right there. Now some of you have noticed a different pattern actually in the table. You noticed that to get from our x, from our blue tiles, to our y, that's times 9. That's a totally valid pattern to find. You just take this times 9, take your x times 9 equals y. That's great. You follow that same pattern. Anyway, back to our graph. Now that we have our dots on here, did I graph this correctly? It looks messy. Oh well, we're going to connect the dots like literally. There you go. And when we have 8 tiles, we're going to take a line and see what matches up from there. So 8 brings us all the way up to 72. Awesome. Just like our table said. Here we go. So when we have 8 blue tiles, we have 72 total tiles. Oh, we never labeled this axis. This is number of tiles in total. That's kind of wordy. How about total number of tiles? There we go. So there you have it. We represented the relationship between the number of blue tiles and the total number of tiles here in a graph, but also here in a table. Let's do one more. Let's represent it in an equation. You notice the pattern in the table right here. That you go times 9, times 9, times 9. So if x is the number of blue tiles and y is the total number of tiles, we'll say that the total number of tiles, oh no, Notability froze again. There you go. The total number of tiles is 9 times the total number of blue tiles. So there you have it. We represented relationships with 2 variables in an equation, in a graph, and in a table. So here's your summary of the day. A table looks like this. We've got x and you've got y. An equation says y equals something times x. And a graph looks like that. Or sometimes it looks like that. Or sometimes it looks like this. So there you have it. Hope you have a wonderful time on your homework.